Okay, let's dive right into this. Welcome to our latest explainer. Today, we're taking a truly fascinating journey under the hood of an AI coding agent. We hear so much about what AI can do, but we rarely get to see exactly how it thinks, how it actually organizes its work, or how it safely interacts with our local environments. So we're going to completely demystify the Claude Code architecture by tracking a single request. We're going from the very millisecond you hit enter on your keyboard all the way to a completed, highly complex task. Now, I know exactly what you might be thinking looking at this complete system map. It is incredibly detailed, and honestly, it looks a little intimidating at first glance. We've got multiple layers, different loops, agent spawners, and data flows just bouncing all over the place. But do not worry, I promise you that by the end of this explainer, this entire diagram is going to make perfect sense. We're going to break it down logically, piece by following what I like to call the journey of a request.
Here is our roadmap for the journey. We'll start at number 1, input and the permission gate. Then we'll move right into number 2, the engine, which covers knowledge and execution. Number 3 is connecting to the world. Number 4, unlocking the multi-agent layer. And finally, number 5, outputs, memory, and observability.
All right, let's kick things off with section 1, input and the permission gate.
Everything literally begins at the input layer with the user interface. This might be your command line interface, your IDE, maybe even a CI/CD pipeline. But the moment you submit that prompt, it hits the session manager. You can really think of the session manager as the traffic cop for your workflow. It has to decide exactly how to handle the state of your request. Like, does it need to resume an old task, fork a current process to try a totally different approach, or just persist the data for later? It ensures absolutely nothing gets lost right out of the gate. But hold on, before any actual work gets done, your request has to clear security. So the absolute crucial point here is the permission gate. And why does this matter so much? Because we're giving an AI access to our actual coding environment. The permission gate uses a super strict 3-tier system of YAML rules: deny, allow, and approve. These rules are your ultimate safeguard. They strictly prevent any rogue or dangerous AI actions in your environment before a single line of code is ever executed. It's just a really fantastic, safety-first approach. Moving right along to section 2, the engine, comprising the knowledge and execution layers. Now, what's really interesting here is how the system handles the massive amount of context you need for coding. The knowledge layer feeds the engine, and it uses something called a context compressor. This is a brilliant 3-layer system with a 92% threshold that essentially just zips up your code-based data. By compressing this context, it makes sure the AI has all the relevant information it needs without getting totally overwhelmed by the sheer size of the files it has to read. Once that context is loaded up, we enter the absolute heartbeat of the entire architecture, the master agent loop. This loop continuously cycles through 3 distinct steps to dynamically solve your problems. Step 1 is perception, reading the input and actually understanding the context. Step 2 is action, deciding what to do about it. And step 3 is observation, looking at the results of that action to decide the very next step. So it doesn't just guess, it perceives, acts, observes, and repeats. Okay, so when the loop decides it's time to take an action, it drops down into the execution layer. This triggers the tool dispatch, which is strongly typed. That means there's one specific dedicated handler per tool. Whether it needs to use bash, read a file, write some code, or grep for a string, the tool dispatch picks the exact right instrument. And it runs these actions in real time through the streaming runtime. This allows for parallel execution, meaning multiple processes can happen all at once, which vastly speeds up your workflow. And guys, here is a number that's going to make absolutely any developer smile. 10%. Let's talk about the sheer efficiency of this execution layer. The system actually utilizes a prompt cache. By allowing for stable prefix reuse, meaning the AI remembers the consistent, unchanging parts of your prompting context, it drops API costs to just 10% of what they would normally be. I mean, that's incredibly fast and remarkably cost-effective. So the AI has thought about the problem, decided what to do, but how does it actually do it?
That brings us to section 3, connecting to the world.
The bridge between the AI's isolated brain and your actual computer is the MCP runtime, and this brilliantly illustrates modular design in action.
The MCP runtime auto-discovers tools. Specifically, it's looking for MCP_server_tool to connect seamlessly with your external servers. We're talking about your local file system, your Git repositories, or even custom internal servers you've set up yourself. It registers these tools so the execution layer can use them, and it writes logs straight to a hidden markdown file called agentmemory.md, ensuring the system always has a complete record of its interactions.
So at this point, we've got a highly efficient, single-agent system that can safely read your files and write code. But I want you to think about this for a second. What happens when a task is just too big or way too complex for one single agent to handle sequentially? That exact question brings us to my absolute favorite part of this entire explainer. Section 4, unlocking the multi-agent layer. Let's see how this magic actually builds out. When a massive task arrives, the sub-agent spawner literally spins up multiple new agents. It's like building a virtual team on the fly. Each agent gets a cleanly delegated task and an isolated context, so they don't step on each other's toes. To prevent overlapping work from breaking your code, the worktree isolator puts each agent on a per-task branch. This ensures zero conflicts. Any issues are just detected later on during the merge. And how do they coordinate all this? Through teammate mailboxes utilizing a Redis pub subsystem for instant real-time message delivery between the agents. Now, obviously, if you have multiple AI agents chattering away at once, you need some strict ground rules, or you just get total chaos. That's where the FSM protocol comes in, which stands for Finite State Machine. It forces highly structured communication. An agent is idle, then it sends a request, then it must wait, and finally, it receives a respond. This rigid flow guarantees these virtual teammates communicate clearly without endlessly looping or talking over one another. But what makes this virtual team truly independent is the autonomous board. Basically, instead of a master agent micromanaging every single step, these sub-agents look at a shared task board and self-assign the work they need to do. When an agent picks up a task, it uses an atomic lock. That means once a task is claimed, absolutely no other agent can touch it. They execute work completely autonomously, safely, and without any human intervention required. Now that our autonomous team has completed the heavy lifting, we need to guide this request's journey to the finish line, which leads us to Section 5, Outputs, Memory, and Observability. The final stop for the data is the output layer. But what you get here isn't just a basic block of text, it is a verified task result. The system actually confirms the action was successful. And even more importantly, this result permanently feeds back into the memory store in the knowledge layer. This creates cross-session persistence, meaning if the AI learns a weird quirk about your codebase on Monday, it's still going to remember it when you start up a brand new session on Friday. And finally, we have to acknowledge the silent watchers. Throughout this entire journey, from the permission gate all the way to the output layer, the observability layer has been running quietly in the background. It uses an event bus to hook into lifecycle events, intercepting and logging data. And it does this using a background executor with non-blocking daemon threads. That's a fancy way of saying it monitors absolutely everything for security and debugging without ever slowing down your main coding tasks. And there you have it, the complete journey. You've just mastered the incredible layered architecture of Claude Code. From strict security gates and 92% compression rates to spawning isolated self-assigning virtual teams that actually remember your codebase across sessions, it completely redefines how we interact with our local environments. So with a secure, highly efficient, and fully autonomous development team right at your fingertips, what will you build next? Thank you so much for joining me on this explainer, and keep